Alright, so now we're in part 2 of question 1, and this one asks us to find a bound on the probability that it lies in a given interval. In question 1 we had to find the interval ourselves. Now we're given the interval and we're trying to find a bound of the probability that A lies in it. So we're trying to find a bound. The probability of A lies within 3, 4. Now in order to do this, let's look at the complement. So let's find a bound on the probability that A lies outside 3, 4. This, just like question 1, we can use Chebyshev's inequality, right? So probability that A lies outside 3, 4 is nothing but probability that A deviates from the mean, which so happens to be 3.5, by greater than or equal to some epsilon, which happens to be 0.5 in this case, right? Oops, you don't want it to be greater than or equal to, you want it to be greater than over here. So you want to find the probability that A deviates from the mean by more than epsilon, because if it deviates by exactly epsilon, it will still lie within the boundary of the interval. Right? I think in question 1 I might have put greater than or equal to, but the good thing over here is that we can directly, or we have a simple relation between this and the probability that the deviation is greater than or equal to epsilon. So the deviating by more than epsilon is an event which is completely contained in the event of deviating by more than or equal to epsilon. So the event on the right has more probability and than the event on the left. So it's going to be an upper bound for this. So we can still use Chebyshev's inequality because now we have a greater than or equal to sign. This is less than variance of A over epsilon squared. So now what we want to do is we want to just calculate this number, and in order to do that we need variance of A. But over here I'm just going to reuse the calculation from last time, which is 1 over n times variance of xi, which is equal to 1 over 30 times 35 over 12. Now this upper bound is going to be 1 over 30 times 35 over 12 times 1 over 0.5 the whole square. 0.5 the whole square is just going to be equal to 4, because it's 1 over half. Yeah, this is simple calculation and I don't think you need me to do this. Which is equal to 3, which is 35 over 30, which is approximately equal to 0.39, 35 over 90. Whoops, maybe I do need to do simple calculation. 0.39, wow. So it's equal to 0.39. So that's what this is going to be, which is going to be approximately equal to 0.39. Oh, I did it again. Okay, so this is a lower bound in the probability that A lies outside the interval. Therefore, the probability that A lies within the interval can be lower bounded. Oh, sorry, this is an upper bound. This is an upper bound for the probability that A lies outside the interval. So A lies inside the interval, and that is with a lower bound of probability of 1 minus 0.39, which is probability of A belongs to 3, 4 with the probability greater than or equal to 1 minus 0.39, which is approximately equal to, well, this is exactly equal to 0.61. So this is our lower bound which we calculate for the probability of lying within that interval using Chebyshev's inequality. And that's it for question 2.